due to that, actually, I think. Okay, so it is being used in material science, in geosciences, mineralogy, this geochemistry. These techniques are being used in environmental sciences like this air samples, water samples, soil samples, etc. And in biological systems and medicines, so this biological samples are also can be this analyzed by these techniques. In industry also, industry quality control, process control, food safety, etc. And in forensic science also, these elemental analysis are used to actually to solve the cases by using these gunshots, etc. Okay, so there are the a large number of techniques are there. So as I told you that I am not aware about all these techniques, but I just have put some names here. Okay. This strip is making a problem.
I'll ask Ashok to help you out, I think.
Okay, now it is visible.
Sir, it is visible.
Yeah, there is some strip is there. That strip is from the Zoom. I am not able to remove that strip. It is showing that.
Okay,
Okay.
सर ऐसे ही चला लेते हैं फिर.
Okay, so they are the classical. Hello.
एक्चुअली दोनों अशोक हो रहे इकट्ठे. कोई नहीं डॉक्टर साहब, चलो आप बोलते रहो.
उनकी ना स्क्रीन में हेडिंग नहीं आ रही. कई बार
अच्छा, let me check it how you can.
I've asked the coordinator, he'll help you out. Just joining back.
Strip.
हेलो.
हेलो. यस.
सर आप इससे उसको जो है ना फुल स्क्रीन ना करके आप वही जैसे पहले कर रहे थे ना सर, दैट विल बी वर्क हियर.
ओके. ओके. In that way?
Yes, sir. Yes, sir.
It's
fine, sir.
It is fine. We are, the whole this thing is visible now.
Okay. Let me just try once. I think now it's okay.
Yes, sir. नहीं अभी भी कट.
हाँ, फाइन. अब इसको
अभी भी
नहीं
प्रॉब्लम
सर,
है.
अभी भी हेडिंग जा रही है सर. अभी भी हेडिंग कट हो रही है सर.
Okay, then let me take only this way. Okay, it's fine.
Yes,
now
sir.
I think.
Yes, sir, it's
Okay.
fine.
Yes, it is fine. इसमें चल रहा है.
So it is now, as I told you that there are a lot of fields are there in which this elemental analysis is being used at present, and mostly it is actually we are interested in this impurities in all kind of samples. Either it's industrial these products or it is a microelectronics, superconductors. So we are always interested in measuring this impurities there, since we want to have a highly impure samples. So for that these kinds of analysis are being used there, and they are the methods are there. Their classical methods is there. These are the things, and there are some instrumental trace analysis and solutions. So for liquids, actually there are some spectroscopic methods like atomic absorption spectroscopy, this inductively coupled plasma optical spectroscopy, this inductively coupled atomic emission spectroscopy. So in all these actually techniques, we have to, these are the destructive type of techniques. In these techniques, mostly the samples are destroyed. Since for these spectroscopic methods, we have to convert the samples into the vapor form. So most of the, in most of the time, the samples is destroyed in these type of techniques. And other techniques are like, okay. As I told you, mass spectroscopy there, same thing. Electrochemical methods is there. So, but I am not much aware of about all these of methods. So, our main purpose is here the instrumentation methods, and there is the X-ray spectroscopy, XRF. But we are not using the XRF itself in our department. One lab is using this XRF techniques for this elemental analysis. But in our cyclotron laboratory, we are using the ion beam analysis, elemental analysis method, and there are the two kinds of actually these techniques, ion beam analysis. In the one technique, in ion beams means we have to use the beam, accelerated beams of the particle, charged particles. So this is the compulsion that in these techniques we should have some this accelerated charge particle beams. So it is a costly affairs, but there are the two kinds of things we can do. One is the profiling techniques, and there is the non-profiling techniques. So in profiling techniques means we can profile the impurities in the sample. Okay, so the profiling techniques have the Rutherford backscattering, the elastic recoil detection and analysis, ERDA, and other is the nuclear reaction analysis. So in this case, nuclear reaction analysis, particle gamma reactions takes place. The other methods are the non-profiling, means we cannot profile the impurities over the sample, but we can find out the concentration of the impurities in the samples. And those techniques are the particle-induced X-ray emission, particle-induced gamma ray emission, neutron activation analysis, secondary ion mass spectrometry, SIMS, charge particle activation analysis. So these are the few techniques which comes under the umbrella of the ion beam analysis. Okay, so here, so what is the ion beam analysis actually? In ion beam analysis, it is based actually on the interaction of the projectile target, this accelerated projectile, and the target material. So there are the two kinds of interaction may take place. That interaction may take place at the atomic level, and it may take place at the nuclear level between the accelerated and charged particles. So, so when this moving charge particle strikes, it can interact with the electrons and nuclei of the material atoms and slow down, and it may possibly deviate from its initial trajectory. So this is the main actually basic principle of this IBA techniques. And what kind of interaction may take place, the type of techniques will depend on that. It may be the elastic scattering, means it may be only the elastic scattering, maybe of the two types actually. Elastic scattering may be like Coulomb interaction, like the Rutherford scattering. So the Rutherford scattering is elastic scattering. Since no nuclear these forces are participating in that interaction, only the Coulomb force, Coulomb field of the protons is and electrons is interacting with each other. So that is the elastic scattering of, and it is Coulomb type. So it is the Rutherford scattering. So, and this technique is used for the RBS, Rutherford backscattering. Others are the nuclear techniques. In this case, in nuclear it is nuclear elastic scattering. So here, the energy of the projectile or the beam is such that it can overcome the Coulomb barrier, and it can interact with the nuclear field. So in that case, it is still elastic, but now the nuclear fields are taking place in the interactions. So there are the two types of scattering is there. Other type of scattering is the elastic scattering. So in elastic scattering, as we know, this residual nucleus is left in the excited state, and that excited nucleus then will decay by the emission of the some gamma rays. It may emit some gamma rays, or it will emit the same projectile. It will deviate the same projectile with the different energies. And there may be the nuclear emissions, and in the emissions, the particles may emit or the gamma rays may emit. Okay. So in the elastic scattering, it is only the, if it is excited, we can detect the gamma rays, and we can detect the projectile itself at different angles. Okay. So what are the positive things, characteristic of the IBA techniques? As I told you, most of the other techniques which are not based on the ion beam interaction. So most of that in those techniques, actually, since we have to prepare the samples, and in that preparation, most of the time the samples is lost, it is destroyed. But here this IBA technique are not generally destructive. So in this case, our samples are not destroyed. So they are suitable for very use with the delicate materials. Secondly, they are to certain extent multi-elementary. Multi-elementary means most of the techniques, as I told you, this ion beam, the other techniques, this mass spectroscopy, etc. In those techniques, actually, we have to decide that which element we are going to detect. So that is a single at one time. In most of those techniques, we can detect only the impurity of the single elements. So in that way, we have to repeat the experiments many times. Okay, and we have to set our experiment in the way that in which elements we are interested as impurities. But in the IBA techniques, this technique is a multi-elemental analysis. Means in a one shot, we can detect all types of you can say impurities in the samples. Okay, and they produce the high accuracy quantitative results. But earlier techniques also, these mass spectroscopy techniques also, they are also good as far as the accuracy is concerned. But the most actually, we can say the most striking or positive points of these IBA techniques is that they are non-destructive, and they are the multi-elementary type. Okay. And second thing, in these techniques, there is very little requirement of the preparation of the sample. Okay. Or in many cases, we can put the sample as such, or very little task we have to do for the preparation of the samples there. So this is one of the positive points of that. Okay. And in this case, we need a very small quantity of the samples. Okay. If it is in milligram also, then we can find out we can do the elemental analysis of those samples. Okay. And secondly, that nowadays we have the PIXE, micro beams also. So in that case, we can analyze the very small portion of the samples in micrometers. So the beam size can be reduced to the micrometers. So, and on that name, there's a name of this one technique is the PIXE. So in that way, the beam size is in micrometers. Okay. So now, so this is I have just shown shown all these things which we have discussed. So this is the incident beam, and this incident beam is striking with the target. In that case, this may be that atoms may be sputtered. This may electrons may be there. It may be beta decays, may be back scattered ions. It may be scattered ions like in ERDA. There may be the X-rays. There may be recoil things, and there may be reactions may be take place. So all these type of interaction may take place, but it will depend that what is the energy of the projectile. Since these reactions or these type of interaction will mainly be decided by the energy of the projectile, which is hitting to the sample. So in that way, Now, second thing that we have to choose which method we have to select the method, which method we have to select. So mainly, first of all, it will depend that what facilities we have. Like in our case, we have the cyclotron machine. So certainly we will prefer this ion beam analysis. But mostly, as I told you, if we can destroy the samples, then we can use these techniques like atomic absorption, atomic coupled plasma, etc., mass spectrometry. Or if we do not want to destroy the samples and we want them, and we are interested in the all kind of impurities in the sample, then certainly we will go with this ion beam analysis. Okay. So let me. I will go to this lecture in the last. Okay. So let me start with the PIXE, which we are doing in our lab in the cyclotron machine. So if there is any question, then please ask in between so that we can interact with each other. So I will start with the PIXE, proton induced. Actually, it is the name of this is the particle induced X-ray emission. But mainly in this PIXE, people are using the proton beam instead of the heavier beam. Generally, all over the world, we are using the proton beam instead. So mainly it is particle-induced X-ray emission, but we can say the proton-induced X-ray emission also. So for this, we need a very low energy, not very high energy, few MeV, like 2 MeV to up to 5 MeV protons. We can use this type of energy for this PIXE analysis, and our machine, as I told you, it is very suitable for this PIXE since we are getting the beam of the protons up to 5 MeV. And nowadays, for PIXE purposes, we have optimized the machine for the 3 MeV. So it is giving the good results. So what is happening actually in the PIXE? So what will happen? The target, it can, when the proton will hit the target, target means it will hit at the atom level. So in the atomic level, it will ionize the atoms, and then the electron will be ejected, and the electron will be ejected from the innermost cell, and that innermost cell will be filled by the outer cell electrons, and in that way, one of the process to fill that vacancy, it is the emission of the X-rays. So one electron, it will come to the lower cell, and the energy difference between the two cells will be emitted in the form of the X-rays. So that is why this technique is called the X-ray technique. So this is I have shown the diagram which I have told you in words. It is just, this diagram is just showing that this is the ion accelerator. It is hitting the electron, innermost electron. It is knocked out the electron. Then what will come? Then the electrons from the outer cell, it will go to the inner cell, and this energy difference between the two will be emitted in the form of the X-rays. So what is the procedure? So we have to catch the X-rays, okay, which are emitted during this interaction. Then we have to measure the number of X-rays, and we have to measure the energy of the X-rays. So the main actually, we can say this characteristic X-rays. So since every elements have their own characteristic X-rays. So once we know the energy of the X-rays, then certainly we can say that from which element this X-ray is coming. This is the fundamental principle of this PIXE techniques. Since we measure the energy of the X-rays, and from the energy, we can tell that from which element this is coming. And if you are interested in the quantification, then we have to measure the number of X-rays. Okay. So let me show you some diagram. This is our cyclotron machine in the Punjab University. So in cyclotron, this is the main machine. This is the main machine, and here you can see these are the two poles of the magnet. So these are the two poles of the magnet, and between these two poles, so the size of the pole of this machine is 26 inch, and where my cursor is there, these are the poles here. So one pole is there, other pole is at this place. So the size of this is around 26 MeV. And in between there is the D. This is the D in between these two poles. So the size, so the size of the pole and the size of the D is almost same, and it is 26 centimeter diameter is the 26 centimeters. Okay. And as you know, as you all of us know that there are the two fields is there in the cyclotron machine. One is the magnetic field and one is the electric field. So the magnetic field is here to actually it is the responsibility of the magnetic field is to keep these charged particles on the circular track, since it is circular accelerators. Okay, there are two kinds of accelerator. One is the circular accelerator, other is a linear accelerator. Like in Delhi, in Nuclear Science Center, International Accelerator Center, it is a linear accelerators. So in the linear accelerator, the particle will travel in a line. It may be like 10 meters or 20 meters. So during that flight, it will be accelerated by the electric field. So it will pass through the potential gradient. And in that way, it will be accelerated. But here, it is, since we have to forcefully keep these charged particles on the circular path. So for that, we are using the magnetic field. Okay. And in the D, and one more important thing, that it is a single D machine actually. People always read the 2D machines, double D machines. So it is a single D machine. So one single D means one D is actually active, on which the potential is being applied, and the other D is it is at the ground potential. So in that way, actually it is not the potential, it is the potential difference which is responsible for the acceleration. So in that way, we are keeping the potential difference, that one D is keeping at the potential, some potential, and the another dummy D, it is at grounded. So in that way, there is a potential difference. So between the gap of the D, the particle accelerated. Okay. But as you know that there is a cyclotron formula, and that formula, this machine, this charged particle must be revolve on the circular motion, and it should come in the gap between the two D in such a way that the front D should attract it, and the D behind that, which is leaving it, it should be repel it. So in that way, this synchronization should be there. So that synchronization, we need an electric field. And as we know, the frequency of the electric field is 50 hertz. We are getting from the source. But here, for the cyclotron, for the acceleration of the particle, we need this frequency of the electric field between around 10 megahertz to 20 megahertz. So we have to convert this 50 hertz to from 10 megahertz to 20 megahertz. So for that purpose, we are using these resonators. So this is the resonator. Okay. So this resonator is actually, it is a big pipe, metal pipe, and it's the whole system is in vacuum. So this part is the resonator part, and this is producing the electric field between the frequency of 10 megahertz to 20 megahertz. And these are the different kind of pumps. As we know that the charged particles cannot move in the air, since if they will move in the air, they will interact with the air and they will destroy it. So the whole system we have to keep in the vacuum. So for that, we are using the diffusion pumps, we are using the rotary pumps. So in the other room behind this, there is a big rotary pump, very big rotary pump. It is around 300 meter cube per hour. And then we are using the diffusion pumps here. And these are the quarter pole magnets. These quarter pole magnets, as you know, are used for the focusing of the beam, etc. So this is in one hole, this is the machine is there, other parts are there on that side, it is not visible. And then from that side, from that hole, then a beam line is coming out, and it is coming to a scattering chamber. So this is the scattering chamber, and in this scattering chamber, actually we can put three types of detectors. Inside this chamber, we can put a charged particle detector if you are interested in detecting the charged particles, or outside the chambers, we can put the gamma rays to detect the photons. So as I told you that we are using this machine for the two techniques, PIXE, proton-induced X-ray emission, and the proton-induced gamma ray emission. So for the X-rays, we are using both detectors are the high purity germanium detectors, and they operate actually at the low temperature, liquid nitrogen temperatures. But this detector is for the X-rays, and this detector is for the gamma rays. So simultaneously we can measure the gamma rays and we can measure the X-rays also. So both are the high purity germanium detectors, but since the energy of the X-rays is much lower than the energy of the gamma rays, so there is the difference of the size of the crystal of the detector. So in the X-rays, we are using a small size detector crystal. It may be around 1 mm or so, and here we are using the big crystal. So this is the main difference. And this is the scattering chamber. This is the rotary. This is the pump. So this whole section of this scattering chamber and beam again is kept at in the vacuum, and the signals from these detectors are going through these cables to the computer room, etc. So now let us see that this is the scattering chamber. This, as I told you, that this is the chamber and this is the inside story of the chamber. So here you can see that the beam is coming actually from this side, from my arrows, where my arrow is there. The beam is coming from that side, and this is the target holder. Actually, it is a circular disc, and having this target holders, the number is around 24. So we just keep the targets here. We stick the targets here at this place. Then the beam will come here. It will strike there, and either it may stop in the target or it may go out of the target. Depends on what is the thickness of the targets here. So, and this is the X-ray detectors. So the X-ray detector is here. So X-rays will be emitted, will be detected in this direction, and this side, this is the gamma ray detector. So as I told you, simultaneously we can measure the gamma rays and X-rays. And why we need the simultaneous measurement of the X-rays and gamma rays, we will discuss that. Okay. So this is just the sketch diagram of the scattering chamber. This is Faraday curve, beam, target holder, this turbomolecular pump, charge integrator, HV detector, and these silly detectors. Okay. Now, actually, now there are the two kinds of samples maybe there. One is the thin samples, or there may be the thick targets, target samples. So it depends on the situation that what type of sample material we have, or can we make the thin samples or the thick samples. So it will depend on those situations. Either we will use the thin targets or the thin means the beam, the proton we will pass through this sample. If the proton beam without much loss, it is very small loss. If the very small loss, if the proton beam can pass through the targets, then we call it a thin samples. But if it is stopped there, then we call it a thick sample. So let us take the case of the thin samples. In case of thin samples, actually, what we are doing actually, what is the methodology to measure the X-rays? So as I told you, the X-rays will come out from the target. It will be detected by the by the detectors, and we have to measure the energy of the X-rays, and we have to count the number of X-rays. So before going to this, let me show you the spectrum, how the spectrum will look like of the X-rays. So this is one of the spectrum. This is one from archaeological sample from the glass. So we are using some glass from the very old civilization. So these samples came from the Iran. So we can see that. So this is we can see that there are different. These are the
Hello, kindly switch off your mic, please.
भाई ये ऑफ करो प्लीज, किसका माइक ऑन है?
रजनी मैम आप भी कर सकते हैं, इनको म्यूट कर दो मैडम। आपको
कर दिया सर
जी।
Okay. So I am just showing you a spectrum that if you hit a sample with the proton beam, then the X-ray spectrum will look like this. So you can see these peaks. So these peaks, the centroid of the peak will give the energy, what is the energy of the X-rays, and if we count the peak area, what is how many X-rays are there. So for that we have to fit this peak. So we have to count the number of count the area under this peak. So count an area under this peak will give the number of X-rays, and the centroid will give the energy. So we need the two things to recognize these elements. We need the energy of the X-rays, and to find out the quantities of the element, we need the number of X-rays. So this is the spectrum looks like this. So let me go to this. Okay. So from here, so this is the formula from where we can calculate. So this is the yield of the X-rays, actually number of counts under the X-ray peak corresponding to the principal characteristic X-ray line of an element is called the YX. So this is the formula. It is the omega is the solid angle, how much solid angle our detector is making there. NP is the number of incident protons that hit the specimen. We know this, and we must know this accurately, very accurately. And Z is the number of samples atom per unit area of the specimen. So Z is the atomic number of the element. So we are interested actually this in NZ, number of the sample atoms per unit area of the specimen. So once we know this, then we can quantify the concentration of the pure impurity in those samples. Sigma X is the production cross-section for the X-ray of interest. So this thing, since we are only calculating the yield, and but we need the production cross sections. So this production cross section actually we calculate with some theoretical models. Some of the experimental values are also available there, but if the experimental data is not available, then we use the theoretical models to calculate this. Epsilon X is the detection efficiency for the X-ray interest. Since this efficiency of the detector will depend on the energy of the X-rays. Since as the energy of the X, so we will get a curve, and if the energy of the X-ray is more, then most of the X-rays may leave the detector without interaction. The efficiency will decrease there. If the X-rays energy is very low, in that case the X-rays may be attenuated in between the target and the this detector. There are some files are there, so it may be attenuated there. Again, the energy of the this efficiency of the X-rays will be reduced. But if you want to find the quantity of the thing, then we must know the yield of the X-rays, which as I told you, we can calculate by fitting the peaks of the X-ray, different peaks. So these quantities, actually we know how for the setup, we know the efficiency. Already we have calculated the efficiency, etc. there. Okay, so once we put the sample and we use that efficiency, and we can calculate the concentration of the particles. So as I told you, we can calculate the concentration of the elements are usually wants to obtain from PIXE measurements for thin specimen the areal concentrations. As I told you, it is mass per unit area. Since in this formula also, as we have done, NZ is the number of sample atoms per unit area of the specimen. So here it will give the areal concentration mass per unit area. Okay, so this quantity we can define in this way. Now, here one quantity is the NP, number of incident protons that hit the specimen, and that quantity actually we have to measure that quantity. So knowledge on the number of protons that hit the specimen and PIXE measurement is required for the quantitative analysis. So it can be measured directly or it may be measured indirectly. Fine. So these are the protons. So what we are doing, we are measuring the current, and from the current we can find out the number of protons. We are collecting the charge, and that charge is give the current. So from the collected charge, from the collected charge, we can find out the number of protons using this formula. So in that way, we can find out the number of incident protons also. Now there are the two types of situation is there. One situation is there that our specimen or our sample is very thin. Okay, so in that case, what will happen? The beam will interact with this and it will pass through. Since the interaction is very, very less, number of incident particles and number of particles which are going to this Faraday cup. Faraday cup is actually the device which is collecting the beam. So from the Faraday cup, we can find out the current from the current integrator. This will go to the current integrator. From the current integrator, we can find the charge. We can find out the charge, and from the charge, as I told you, this formula, we can use the number of particles. So approximately, but very good, 90.99%. Since you know this cross section is very large. It is in bond. If it is in atomic interaction, then the cross sections are in bonds, few bonds, 10 bonds, 100 bonds. Okay, and if it is a nuclear physics, then the cross sections are in millibonds. So it is showing that very few particles, incident particles, are interacting with the target, with the sample, and most of the particles are going through the sample and they are being collected on the Faraday cup. So the number of collected particles on the Faraday cup are equivalent to the number of incident particles with very less error. So the Faraday cup we will use if the sample is very thin. Okay, if the sample is not thin, then we have to collect the current from other sources. Okay, so this is the formula for the X-ray cross sections. Okay, so as I told you, it may be the since X-ray production cross section is produced by three factors: sigma I, omega I, fx. But the sigma I is the IS style. It is the ionization cross section actually. Okay, and omega I is the fluorescence yield, and fx is the fractional radiative width of the X-ray line. Actually, once a vacancy is created, then it may be filled in mainly in three ways. Either it will emit the X-rays, or it will emit the Auger electrons, or it may be this other type of interaction. Other type of interaction means the electrons may come from the other cell to fill the vacancy. So there are the three processes, but we are measuring only the fluorescence yield, since we are measuring only the X-rays. So this X-ray photon is emitted during this vacancy. So we are measuring only this part of this, and those other parts, since we are in test, we have to find out the total production cross sections. So for these parts, we will use some theoretical models to find out this. So in this way, we will use this. So this is the just a spectrum of the X-rays, like it is the K cell, L cell, M cell, N cell. The different kind of cell is there. So it may be that the most of the probability is that when a proton or charged particle it will hit, it will actually eject the electron from the innermost cell, K cell. It will emit, and since the probability for the higher cells is lower, so it will emit from the K cell. Then one vacancy is there, and that vacancy will be filled from the electrons from the L cell, and there are the three cells is there. So alpha 1, alpha 2, alpha 3. Actually, I'm showing 2. Then it may be filled from this M shell. It may be filled from this other cell. So in that way, it is if the vacancy is in the K shell, okay, so this will be filled by the electron from the L cell, and we call them the K X-rays. If there is the vacancy in the L cell, then those vacancy will be filled from the electrons from the outer cell, from M cell and N cell, and those X-rays are called the L X-rays. That is, and similar way the M X-rays, N X-rays, but they are not important for our purpose for this elemental analysis. The main purpose is only K X-rays and the L X-rays. And most of the times for the lighter elements means if the atomic number is around Z is equal to 50, then mostly we use the K cells, K X-rays there. If it is heavier element, then we use the L X-ray elements there. So there is certain, so we know which X-rays from which element we have to use. We have the chart of that, and we just select, check that X-ray in the spectrum. We find the energy, we count that X-rays. So in that way, we can find out the fluorescence yield from this. Okay. Now it is a detection efficiency. It is very important, as I told you, since suppose the 100 X-rays are produced in the target, since our detector is seeing only a very small the solid angle, since 4 pi solid angles, we are just actually this covering only maybe 1%, not one, maybe around 1% or less than 1% solid angle. So most of the electrons are going away. So we are detecting very little number of electrons. But for those electrons also, since every X-rays has a different efficiency. Suppose they are the X-rays of 2 kV X-rays. So that 2 kV X-rays have the different efficiency. Suppose 100 is coming, let us say the detector is counting only the 40 there. suppose it's a 4 kV X-ray. In 4 kV X-ray, let us say 100 is coming, it is detecting 60 X-rays. Suppose it is a 10 kV X-ray, in 10 kV X-ray, let us say it is detecting the 20 X-rays. So in that way, we have to make the efficiency correction in the detector. Okay, fine. So this is the formula, we can use that. So these are the features. As I told you, the feature is that is multi-elemental analysis. Okay, it is non-destructive, no damage, high sensitivity, 0.1 ppm for thick samples. We can go up to the 1000 angstrom. It will depend on the energy of the proton actually. Since higher the energy of the proton, more it will penetrate to the sample. But still we are calculating, we are measuring actually impurities only on the surfaces, since there is a limit on the penetration of the particles. Now it is quantitative without standards. We can use the standards or we can use the without standards. And as this technique is actually we can use only, this technique is sensitive only for the approximately Z greater than 13, like silicon. From the silicon we can use this technique from onward silicon. For lesser, if the impurity is lighter than silicon, then this PIXE is not sensitive to that, since the energy of exchange energy are very less, and they will be actually attenuated in the path between the target, in target itself. Some will be attenuated, in some will be attenuated in the target, in this detector, etc. So this PIXE technique is not useful for the lighter elements. So for that we will use the other techniques. If the impurity is of light less than the Z14. So this is, as I told you, this is one of the spectrum for that. These are some spectrums. So these are the, let me say, these are the typical, these are the some main features of the spectrum. Since there will be the, as I told, they are the, they are the peaks are there. Okay, but they are the, this is the, background is there. Okay. So background is there. Background is always at the low energy part of the X-ray spectrum. Fine. So they are the different contribution of the. You can see at the higher energy there is no background. It is very smooth. But at lower part there is a background noise is there, and sometimes the X-rays with small quantities are actually maybe just may not be actually clear in the background if the intensity of the X-ray is very less. But this, and what is the region of this background? The region of the background is there are the three regions of the background. So main region of the background is the secondary electron bremsstrahlung. Since when this target it will hit the material will get ionized, electrons will be emitted, then those electrons will again interact with the electrons in the material. In that way, secondary electrons will be there, and those secondary electrons will be de-accelerated. And as we know, when a charged particle is de-accelerated, it emits this radiations. So those radiations are due to the bremsstrahlung radiations. So most of the part here in this background is due to the electron bremsstrahlung. So there may be the projectile bremsstrahlung also, but projectile bremsstrahlung is very less. As let me show you this figure also. So this is the figure. This is the secondary electron bremsstrahlung. So we can see at lower part, this is very high, up to let us say 4 MeV. We can say up to 4 MeV or 3 MeV, 3 kV. This background from the secondary electrons is very large, so it will disturb the spectrum as it has disturbed here in this case. Okay. So there may be, like we can see, it is disturbing the spectrum here. So this is mainly due to the
ये प्लीज म्यूट कर लीजिए, बाकी लोग कौन बोल रहा है भाई ये?
Please off your system.
Okay, so this is the, so these are the, so that we can see this, the spectrum is not good here. Here, there's a lot of background is there, and this, and the region of the background is, as I told you, secondary electrons Bremsstrahlung, proton Bremsstrahlung. But since the mass of the proton is very, it is much heavier than the electrons. It is 1836 times the mass of the electrons. So in that way, this background is very less due to the proton Bremsstrahlung. But there may be the gamma rays also, which are produced by the excited nucleus. So some background will be there due to the, but it is a constant background due to gamma ray. So this is, you can see, this is the total background, and you can see the most of the part of this background is coming from the gamma rays and from the secondary SEBs. Okay. Now, if you take the the thick samples, then in thick samples, actually, it is difficult. There is a considerable loss of energy will be there in the target, and the X-rays will also be attenuated in the thick targets. So and there will be difficulty in monitoring the number of incident particles, means since the beam will be stopped in the target itself, in the sample itself. So we cannot measure the current, we cannot measure the number of projectiles from the Faraday curve. So we have to do some other things here. Now, if the target is insulating, then there is a built-up charge on there, and it will again contribute to the higher background. Okay. So, so generally, what we do, we actually make the target the conducting targets. So in that way, once if the target is conducting, then there are the two benefits of that. One, we can if the target is thick and it is conducting, then from the target itself we can find out the charge due to the incident protons, or we can find out the number of particles due to the incident particles if the target is conducting. Secondly, it will not be heated up, since the charge will not be built up if it is conducting. The charge will go through the other sources. So generally in our lab, or in the case of PIXE analysis, we always try to make the target as the conducting targets. Okay, so for the thick target, we have to apply some other techniques, since there is energy loss. So instead of that earlier formula, we have to use this formula. Most of the things are same, but this is the, now it will be the target. It will depend on the matrix of the sample, and since the loss mode will be there, so at every layer, so in that way we have to divide the sample in the very, very small thin layers, and then we find out the energy losses of the particles, and in a particular thin layer we take the particular energy, and for that we calculate the cross section. Then we take the second layer, the energy of the particle will be different, since the cross section will depend on the particle, it will depend on the energy of the particle actually here. So that is why this integration is due to that. So we are just slice the target in a very, very thin samples, and we just integrate it, and we find out the cross sections, since we are interested in the cross sections there. So this is the one of the techniques. So if the target is thick, as I told you, then we will not use the Faraday curve, we will use the chamber itself. So in that way we will make the target conducting target, and then that target will be directly connected to some charge integrator, and then in that way we can measure the charge collection. So charge collection is very, very important. If we could not measure the charge very accurately, then our results will be very vague. So we have to measure the charge collection or number of incident particles very accurately. And another method may be there. If let us say if our sample is not conducting, and we cannot make it conducting, since if it is not conducting, then we have to make it conducting, and for making it to conducting, we have to destroy it. Then we have to make the powder of that sample, and we have to mix the graphite, since graphite is a good conductor. So in that way we make the conducting target. But if you are not in a position, we cannot afford the destruction of the sample, then we have to apply some other techniques. If it is some glass is there, or some other things is there, or some book is there. There are so many actually these artifacts is there in which we can measure these things. So in that case we have to measure the other techniques, and that technique is that we will detect the scattered particles at back angle, and from there we can measure the incident particles. Or what we can do, one more thing, we can put a carbon file before the specimen, before our targets, and from the carbon file again we will, this thin file we will put, so that the energy, since carbon is a low Z element, so the loss of the protons will be very less, energy loss will be very less. So the particles will be scattered again, and then we can detect. So these two techniques we can apply if we cannot make a sample, a conducting samples. So these are the two techniques to measure the this. So this is the, so let me, so this is the methods how we can reduce the background subtraction. Okay, so these are, we can making a target electric, as I told you, these things I have already told you. So these are the few things using we can make the targets as conducting targets. So, as I told you, these applications, so this may be used in paint. If there's, suppose they are the very old paintings, maybe suppose let us say 1000 years old painting, and we want to know that what was the components of this painting, since if we do the elemental analysis of that painting, then we can come to know about many things of the history. So the archaeological samples, actually, we, by elemental analysis, we can correlate the concentration of the elements with the historical with the history there. So a lot of the historians use actually these things, these samples, to use the PIXE, to use the PIXE, like the painting, it may be the manuscript there. And in case of manuscript, we can use this in the forensic also, since the different inks have the different compositions. So if you put the paper before the beam, then we can find out that what is the composition of the ink, and from that composition, we can find out that this manuscript is original or it is fake, or which pen have been used for that. So we can see the forgery, etc. We can use the pottery samples. Pottery sample, again, it is from history point of view. These are very important things. Sculpture, coins, ceramics. So all these samples are of the historic, for the important from the historical point of view. Or we can use the biomedical samples, tissues, blood, hair, nail bone, tooth. So suppose, so these samples we can use to just to correlate that if in some particular area, suppose some special kind of disease is there, then we can, from the patients, we can take the samples, blood samples or hair sample, tissue samples. Then from those compositions, we can find out that which elements those people are taking more in those areas. So in that way, the doctors can correlate these things with the this medical history. Okay, environmental sample, as I told you, we can use the aerosol, water, soil sample. In forensic, again, glass, painting, ink, security paper, etc. These are different kind of samples. In semiconductor industry, we can use this in semiconductor industry also. For purification in food industry, we can use these techniques. In soil samples, in geographicals. So these are the all these. So we can see that this technique is, we can use, I think, in almost all kind of samples we can have, we can think about. So we can use these PIXE techniques. And as I told you, suppose we are interested in this painting. So as I told you another time, these techniques, some of the techniques which are this mass spectroscopy based techniques. So there we have to destroy the samples. So we have to make the sample there. So in that way, you have to destroy the painting. You have to take some part of the painting. So nobody will allow. Suppose it's a 1000-year painting, nobody will allow you to destroy that, to take the sample. But here we can use the painting as such. We can put this painting in front of the beam and we can find out the access. The techniques are there. So we can use the beam in the open also. Fine. So this is the main thing of these PIXE techniques. And we got some samples 2-3 years back from the Iran. So these are some glass samples there, and some historian sent us these samples there. So then we find out this, we analyze these data, and then we find out these different elements. Since, as I told you, we can recognize these elements from the energy. So these different kinds of elements we can measure. And actually all these things, this spectrum, etc., we use the GUPIX program. So it's a lot of theoretical things you have to do in that. So we use the GUPIX program. So we provide this experimental spectrum to the GUPIX, to the spectrum to the GUPIX, and that will provide this elemental concentration. So these are the different kind of samples. This is samples is again from this sample is from the water sample actually. So you can see we take the distilled water. First we take the sample of the distilled water, and we can see there is not many elements are there. Only few elements. This iron is there, little bit iron is there, K alpha, K beta is there, and some zinc is there. So no other impurity is there in that sample. But when we take the actual sample of the water, then you can see that there are a lot of elements are there, and many elements are very actually this dangerous for the health purpose. So in that way we can take the, so we have done a lot of analysis for the ground samples from various places, like in Punjab, from this Haryana, from Hindon area. So we have done a lot of analysis there to find out what are the sources and what are the impurities there in the samples. Okay, so now the next technique is that is this, as I told you, that this PIXE techniques we can use only for the elements which have the heavier elements, which have the Z number greater than much, which are heavier, more heavier than the silicon, or silicon or more heavier than that. So these techniques we can use there. But if you are interested in the lighter elements, then we cannot use their techniques there. And so we have to adopt the proton-induced gamma ray emission. Okay, then proton-induced gamma ray emission, as I told you, these emissions are actually, these techniques are useful for the lighter elements. And what is the PIGE? Actually in PIGE it is only the atomic level interaction, but in the PIGE it is the nuclear level interaction. So here the incident particles are interacting with the nuclear field, and they are exciting the particles, and those particles then excited will be in excited states, and they will decay by the gamma rays. So we detect those gamma rays, and other method is in this same method. Then this is the formula for that. So this is the gamma ray. We have to find out the cross sections for that. So these are yield is there. So this formula we use, this is the sigma r, is the proton Rutherford cross section from you. Actually what we are doing, since we are detecting the numbers here only, so that number we have to convert actually in the we have to convert to the cross section. So to convert the number, since we are detecting the part in the detector only the number of particles, how many gamma rays are coming, but those gamma rays are not so useful. So for that we have to convert those gamma rays into the actually cross sections. So this is the formula for that. So once we know the cross sections, then we can find out the concentration of the elements in the lighter elements in the this PIGE this samples, and we can find out like lithium, we can find out carbon, we can find out carbon energy very high, so we don't use carbon for this purpose, but sodium, magnesium, so those elements, fluorine is more important from the point of view of the water, since fluoride is dangerous for the health or teeth, etc. So those elements cannot be detected by PIXE, and in other techniques also it is difficult to detect those elements. So this proton-induced gamma ray emission will be used, and I will show you just these gamma ray spectrum. So these are the peaks again, and these peaks are for different these elements. Once we know the energy, then from the energy we can find out that this gamma ray may come from which elements. So as I told you, this gamma ray is from the aluminum, these are again from the aluminum, this is the fluorine, this is the sodium. So sodium is sodium, this is the lithium. So in that way, so this is the typical spectrum of this gamma ray. So we have done a lot of archaeological samples and this water samples using this gamma ray techniques, PIGE techniques for that. And this is from the aerosol samples. Since in aerosols also these elements are there, so we can find out the concentration of those elements. So as I told you that we are just using this type of method, but the material science people can also use who are interested in the actually quantity or in the purity of the samples. Like in electronics industry, the purity matter very much there. If very little impurity can cause a lot of problems there. So these techniques can be used there. And in foreign countries, actually, there's a lot of interaction between the industry and these people who are doing these techniques are there. But in India, it is still, we are not at this level. There is very little interaction with the industries since. So, okay, so this is the evaluation process is there. So these are the two techniques are there. Okay. So how much time I have?
So you have another 10 minutes, sir.
10 minutes. So, okay. So let me just introduce very little about this this RBS, recoil distance backscattering, Rutherford backscattering. Since we are planning to start this Rutherford backscattering here at our lab also, but in IUAC, they have the small accelerators and they are using these techniques there, RBS techniques, Rutherford backscattering techniques. As I told you that we can do the profiling with this technique from this Rutherford backscattering. With PIXE and PIXE, we cannot do the profiling actually. We can find out the concentration there. So the main principle of this Rutherford backscattering is that, as the name suggests, that it is the backscattering. Back means beam is coming at, this is our sample, beam is coming from this side. So we have to put this detector, this is a detector which is detecting the charged particles, alpha detectors. So we have to put that backside. And why we are putting the backside? Since the one of the main reasons that at the backside there is very less background is there. In the forward, there is a lot of background is there. So we always prefer, it is a very clean area. So we always prefer the backscattered alpha particles. So this is the silicon detector. Generally, we use the silicon detectors here, but there is some actually problem with the silicon detectors. It is since the resolution is not much, but even for this purpose, we can use this. For RBS purpose, we can use this detector. And what is the main factor? Actually, what is the methodology? I will just tell you what is the methodology of this Rutherford scattering. Here is the one factor, is the K factor, it's the kinematic factor. This is the most important factor which will decide that is the ratio of the scattered alpha particles energy to its incident energy. Gives a convenient method for determining the elemental makeup of the target atoms in the sample. So to determine the K, so this is the formula for the K. So I will not go in the detail in the formulas. So again, we can find out the formula. So let me tell you how this formula is changing with this K value. So this is the K factor actually. So K factor is changing with the elements. So this is the hydrogen. For the hydrogen, this is the actually K factor. And this is the mass of the, actually it is the mass of the M2 target. So for the helium, it is this thing. For helium, this one, 12 neon. So in this way, for different elements, this kinetic factor is changing, and this is the main factor of that. So let me come to, okay, so this is the one of the figure. So this is the figure. From here we can measure the delta E. So we can measure the thickness determination from the thin sample. If we have a very thin film, then we can measure the thickness also from the Rutherford backscattering. But generally we do not use this for a single film. We always use this these techniques for the, if we have a sample in layers. So if you have the sample in layers, then we can find out the, and we can find out the concentration, and we can find out the elemental this recognition of those layers. Like this is the layer here. So it is a sample. In this sample, and there is one more thing that in this sample we can see that there is some actually these restrictions when we use this Rutherford scattering. To get the best results, what we have to do, the substrate should be of lighter elements there. So this is the main condition here. So there is a substrate of silicon, and on the substrate of silicon there is a tantalum surface there. So we can see that how the spectrum will look like this. So this is the tantalum at the surface, and this is the then it will be silicon, and then it will be this type of reaction there. So this is the typical spectrum of the backscattered particles. Okay. And if you have the multi-layered is this let us say these samples, like here the oxygen, sodium, silicon, K, Z, and CD2. So again, we have made these layers on the, let us say on the some lighter lighter than this. It should be on, let me maybe carbon or so, I don't know. But like the, so it is, now it will give the cadmium, zinc, potassium, silicon, sodium, etc. So these are the basic characteristic of the Rutherford scattering. And typical application is the, if you are interested in the absolute thickness of the films, coatings and surface layers, surface interface, contaminant detection. So these are the different techniques we can use. These are the different information we can get from the Rutherford backscattering. Okay. So I think from my side it is over. So if there are any questions.
Thank you, sir.
Okay. Thank you very much.
One minute, I'll ask the audience. Anybody who want to ask any question related to what sir has said? Actually, you have opened us up a new platform for me. Actually, I am from a field of experimental condensed matter physics, basically. So I never knew that we can do this elemental analysis by using this different ion interaction technique. So I think now I can start up something new also along with my work, which I'm already doing in my research. So it was a very wonderful lecture. Sir, I would like
Thank
to
you.
ask one thing. You were talking about a thin target and a thick target.
Yes.
And as far as I could understand, thin target is the one from which the proton passes, and thick
Yeah.
target is the one which does not pass. So
Yes.
before placing the target, can we not determine by the dimension whether it's a thin target or a thick target?
Generally, actually, we can measure the thickness of the sample.
Mm.
First of all, in most of the cases, we know the thickness. Suppose we do not know the thickness, but at least we have some idea.
Mhm.
And mostly, like in, if we made some sample, like in our nuclear physics program, also we make some thin samples for this nuclear structure or nuclear reaction things. Okay, so we get some idea from this when we actually make the target by the evaporation, by measuring the how much area it covered and how much was the target. Some idea we have, but we can measure the more accurately with the alpha scattering. So if we pass the alpha, so we just use a very simple setup. But if we can measure only thin, if it is only single thin film is there. So we just get the energy of the alpha particles without film, then we insert the thin film. So the alpha particle will lose the energy, and from that loss of the energy, the difference of the energy, we can measure the target thickness. But from the XRF, ED-XRF also, like Professor Mehta, they are doing the ED-XRF things. So many people come from the like IUC, if they are interested in measuring the target thickness, so they can measure the target thickness. But here we can find out that when we will put the target there in the ladder, and if something is coming on the this Faraday curve, then it means it is passing through that. If nothing is coming, it has stopped everything in the targets. So for that, as I told you, we have to apply 2 or 3 techniques. Since that charge measurement is very, very important, and we have to measure it very accurately. Otherwise, our results will not be correct.
And when we are having an ion kind of an interaction, why the sample is remaining as such? It is not being destroyed, or it is not having any kind of a loss associated with it. That's what you're saying about it. So
No,
what happens? Generally, we
there-
take when an ion is incident on a material, then
yeah, there may be radiation effect on that sample if we actually irradiate it for a longer time. But here, if you put the sample, I think if you just in PIXE, I think in 5 minutes we can get the lot of X-rays.
okay.
So in that way, there will be very less damage is there.
Okay.
People are doing there, like Professor Tripathi also did some experiment in cyclotron for this damage, this irradiation purpose. From Gujarat, one is Professor Anil Singh. I think he used a lot of beam time there in cyclotron for this irradiation purpose. But here in PIXE, since you have to check for different times. But in PIXE, most of the things we are doing here, actually we are not much interested either there is some radiation damage or not there. Okay, but if someone is interested that we have to save this sample from the radiation damage, then we have to actually then radiate it for a very small time. Since X-ray cross section is very, very large.
Okay.
Yeah, that's
So
what
in a
I'm
small
saying. That
time-
contact, Ashok, I think contact time will matter here. For how much time the contact is with the target.
Yeah.
Mhm. Okay, sir. Thank you very much.
Thank you.
Thank you very much.
Thank you
It was
very
wonderful
much.
interacting with you.
Thank you for inviting me. Thank you. Thank you very much for giving me the chance. Thank you. Thank you very
Yes,
much.
sir.
Thank you very much for a
Okay.
nice presentation. Really, it was wonderful.
Okay. Okay. Thank you. Thank you very much.
Thank you, sir.
Okay. Bye.
Okay, now I would like Dr. Vinod to. Dr. Vinod is there in the.
Yeah, ma'am.
Okay.
Good noon, ma'am.
Okay, let sir close the screen, then you can share.
Shall I share? ma'am?
Sir, there is one
Yeah,
question.
Avin.
Sir, there is one question from the audience.
Okay, okay. Dr. Ashok? How are you?
I think if it is not there, you can email him.
Sir is in the meeting.
Okay.
Okay.
Okay, then should we start the second lecture?
Yes,
The
ma'am.
question can be sent on email.
Yes,
You
sir.
send it
The
on
question
email
can
and
be
we can
sent on
get
email too.
reply. You will get the reply.
Yeah.
Okay, Dr. Vinod, you can share
Yeah,
the
that's-
screen if you want to.
Yeah, sure, ma'am. Just I'm sharing. Just. It is visible, ma'am.
No, it is yet not visible.
अभी तो आप दिखाई दे रहे हैं अभी तो अब आया
जस्ट एक शेयर कर चुका मैं आई थिंक
अभी जस्ट फुल स्क्रीन कर दो विनोद.
अच्छा
होगी है सर.
होगी है. ओके.
नहीं है आपका
हाँ,
वो भी
अभी full screen,
लैपटॉप का भी सारा आ रहा है.
जस्ट a minute, मैम. हाँ जी, अब विजिबल है मैम फुल स्क्रीन.
ठीक है.
Okay, good noon all of you.
Let me welcome you first.
It's okay.
Okay, on behalf of the department, I welcome Dr. Vinod Kumar. He is presently an assistant professor in Department of Physics, D+ Moorsal. And
there was a Madam Rajni, there was a message from for earlier talk. I think attendance link is not working. Somebody gave this message.
Yes, sir. I am working on that.
Okay.
Maybe there is some technical error because I have not switch off the attendance, not activated from here.
Okay, you do it, please.
Yes,
no
sir. I
problem.
am doing that.
Go ahead, Rajni, madam. Go ahead.
Okay. So now I welcome Dr. Vinod Kumar. He is presently assistant professor in Department of Physics, D+ Moorsal, and he has recently been appointed as associate professor in NSIT Dwarka. So we are having him for a few days only, and is one of the gem of the department. Does lot of research work in ferrofluids. He has got 50 publications in international reputed journals, 2 patents to his head, and he has filed 2 more patents. Actually, he actually works in the experimental part, and he's basically interested in finding the application of the ferrofluids. He has worked on ferrofluids for a long time, and now he's basically working on finding a application for a layman using ferrofluid. So this lecture will be very useful for the students who want to work in the magnetic material, and he's one of the best person to refer to if you are working in magnetic material. So in addition to what he's going to tell you, you can ask anything about magnetic materials, and he's a master in it. Rather, he's an encyclopedia as far as the magnetic material is concerned. So now I welcome Dr. Vinod Kumar, and Vinod, you can start your lecture.
Okay, very thanks, ma'am, for your kind words, and thanks to all the organizers as well as the participants who are paying keen interest towards the lectures delivered during this FTP program. And all the lectures are really very good and very much very much increasing our knowledge. So in this series, I'm also going to present my work on the nanomagnetic materials, ferrite particles, and magnetic fluids for their device applications. Okay, I will discuss some device applications of these magnetic fluids. And these devices, when you hear that these devices are very simple, and everyone, even a layman or a student or any teacher, they can work on these devices. They can further enhance these efficiency or then develop their new devices. Because there is some properties of these fluids that are very useful in the development of these devices. So I'll start with my presentation with the introduction to nano in magnetism. So nano in magnetism, when magnetic particles, when we reduce the size of magnetic particles below 100 nanometer, nano by definition, you are aware that below the size of 100 nanometer particles, we are called these particles as nanoparticles. Nano stands for -9 meter. And so in magnetic materials, especially in magnetic materials which form the domains, means ferromagnetic, ferrimagnetic, and antiferromagnetic materials. There are other diamagnetic and paramagnetic materials also, in which there is no domain formation. But in magnetic materials which form the domain structure, domains means alignment of some magnetic moments of combined in a particular direction. So in the sizes of 100 nanometer, the particles are multi-domain particles. Multi-domains means there are more than one domain. You can see in the picture that there are different directions the domains are being aligned. But as we reduce the particle size at a certain limit, it's approximately 40 nanometer, it may be 45 nanometer for some other structure also. Okay, it may be 35 nanometer, approximate 40 nanometer, the particles are single domain particles. And if we further reduce the particle size, we call these particles as super paramagnetic. They are, even if they are ferromagnetic or ferrimagnetic, they show the paramagnetic behavior. So we call these the paramagnetic words from here, that because they show the paramagnetic behavior means they have zero coercivity and zero retentivity. And the super word is because of that their magnetization is high as compared to paramagnetic particles. So these are some different size of particles that we call bulk. Above 100 nanometer, the particles are bulk magnetic particles. So in general, why we study nano? Because there is a very large change in the properties of nano as we reduce the size below 100 nanometer. There is in almost all of the property changes very much. Means even if for the magnetic particle, the magnetic property changes. A particle which have high magnetization may of 100 nanometer particle may have high magnetization. 10 nanometer particle may have reduced magnetization. 40 nanometer particles may have high coercivity. 10 nanometer particle may have zero coercivity. And similarly, other properties, electrical properties also, color also, like silver. Silver is best conductor, but as we reduce the particle size to 50 nanometer or 25 nanometer or 10 nanometer, it becomes insulator. Also gold, the color of gold is nearly yellow in case of bulk gold particles. But as we reduce the particle size below 100 nanometer, 15 nanometer particle may have brown color, 25 nanometer particle may have some green color or some. These are dependent upon the shape and size also below the 100 nanometer. Above 100 nanometer, there is not much change in the properties. Silver is the best conductor above 100 nanometer. But below 100 nanometer, there is a very much large change in electrical, magnetic, and optical, almost all of the properties. So it is very interesting to study these size of particles. And we have studied the nanomagnetic ferrite particles especially, and also seen the application of these particles. We have also developed the magnetic fluids from these particles. And I would like to define the fluids, some of the aware about these magnetic fluids. But what are the basic constraints of these fluids? These are using these nanoparticles. Nanoparticles means below the 10 nanometer particle for the ferrite fluid. Okay, nanoparticle 100 nanometer below, we call this nanoparticle, but below the 10 nanometer particle, because higher size particle, what will happen? They will, due to their larger weight, they will get settled down in the end. Magnetic fluid basically consists of 2 to 10 nanometer magnetic particle coated with surfactant chain and then disperse in some liquid. They are basically, they have both the properties magnetism as well as fluidic, means they are attracted towards the magnet and they can flow also. So we call these as fluids also. And what creates magnetism in these magnetic fluids is the nanomagnetic particle of size 2 to 10 nanometer. What is the role of surfactant? That these prevent, because individual particles are individual magnets. If you see that in a single domain particles, all the magnetic moments are aligned in some particular fashion. One end is the north pole and other end is the south pole. So north and south of one particle may attract the north, south of one particle may attract the north of other particle. So they may get agglomerate. So to prevent this agglomeration, we coat these particles with surfactant chains, some materials like we are using oleic acid for this C17H3COH chain. Okay. What it creates, that its length is about oleic acid. The length of this chain is about 2 nanometer, and it acts like a spring. When some other particles came in nearby it repel. There are two. One is the polar head of the surfactant chain, which get attached to the magnetic particle with the help of small electrostatic attraction, and one non-polar tail that is in the liquid, dispersed in the liquid, that also favors the bonding with the carrier liquid. Carrier liquid may be water, it may be kerosene oil. As per our need, we may change the carrier liquid. So these magnetic fluids have both the character that they are magnetic also, and they can flow also. So these we develop also from the particle size, 10 nanometer particle size, ferromagnetic particles or ferrimagnetic particles. Then we see the application of these nanomagnetic particles and especially the magnetic fluids. We have in our laboratory, we have studied about these applications in the energy sector. We have developed wind turbine and increased the efficiency of existing wind turbines. Okay. Although it is at present, it is a lab scale model. Okay. It may come in the future in the large scale wind turbines also. Sensors applications we have developed and patented also: temperature sensor, vibration sensor, acceleration sensor, humidity and alcohol sensor. These all we have developed, studied in our laboratory, and some of these are patented also, and they may become in the device, may come in the near future also in the market. Memory storage, there is single domain particles and multiferroic materials. Multiferroic materials we are also going to add in these ferrite particles to enhance their memory storage applications. And single domain particles are used for the memory storage because they have the high corrosivity and small in size, and having high corrosivity particles are very best for the magnetic memory storage applications. Magnetic cooling applications in the self-cooling without energy, and in the transfer core, cooling of the transfer core. Some of the applications Professor Sani has already discussed in the morning session, self-cooling application, especially they have discussed in their lecture. MEMS-based devices, we have used these magnetic fluids in the design and development of micro valve and micro pump. And then EMI shielding, these materials, nanomagnetic materials are very also good with small altering their properties. We can use these materials for the micro absorption applications also. So this is the basic synthesis chart for how we synthesize the nanomagnetic particles in our lab and synthesis of the magnetic fluids. Okay, and this is a very simple method, and the basic constraints are very simple salts. So everyone who is interested can develop these nanoparticles by studying a little bit literature, and with the help of very small equipment, salt plate, and just like this, using the some simple salts. So you can develop the nanoparticles, nanomagnetic ferrite particles. And initially what we take the salt solutions in water, just a simple water. We take the salt solution, distilled water means, and then we mix this salt solution. For example, we want to synthesize Fe3O4. So in Fe3O4, we have Fe2 positive, Fe3 positive. We take the salt solution of Fe2 positive, salts mean FeCl2, okay, or FeNO3. These are the salts basically. And for Fe3, we take FeCl3, FeNO3 thrice. Okay. And these are, they get dissolved salts, because the salts get dissolved in the water. So by taking the salts, water aqueous solution of these salts, and then just simply after taking the solution, we just mix these salt solutions, and we put some oleic acid so as to prevent agglomeration between these particles. And then we precipitate using the ammonia solution, because it has the high pH, and as the pH of this solution increases, some chemical reaction happens, and with that chemical reactions, the particles get precipitated, particles get formed and get precipitated, and you can get the finally nanomagnetic particles after drying on a simple hot plate. Then if we mix the kerosene, it acts as like a carrier liquid, and we will get the magnetic fluids. So the stability of the fluid depends upon the size and the uniformity of the particles. Means if the particles are less than 10 nanometer, and if they are coated properly with the oleic acid, then we can get a stable fab fluid. If the particle size are higher size range, then they may get settled down. So we can also prepare magnet fluid. However, it is a little bit tricky. Making fab fluid is a little bit tricky, because sometimes we don't get homogeneous particle size distribution. So with the practice, we can develop a good fab fluid also. So this I would like to initially in the first slide, I would discuss that there are many in this 10 to 100 nanometer size range. We have many like super parametric particles, single domain particles, multi-domain particles. So how to get these particles, 10 nanometer particles, how do we get? How we get the 100 nanometer particles or 40 nanometer particles? As we have already learned that we can synthesize the nanoparticles of 10 nanometer size. If we anneal these particles, anneal means heating at these particles inside some using a heating device like furnace. So if we heat these particles at temperatures, initially the particles we dry at the hot plate at about 100 degrees Celsius. When we heat these particles at 300 degrees Celsius, 500 degrees Celsius, higher temperature, whatever temperature, 700, 900, because these are ferrites, already oxide. This is the particle we have taken, cobalt ferrite. This picture we have taken for the cobalt ferrite. This shows that electron microscopy graphs of, because using the electron microscopy, you can see the nanoparticles. Optical microscope, you can see the microparticle, but you cannot see nanoparticles. Using electron microscopy nowadays, HRTEM also, which you can see the atomic lattices that you can see from the HRTEM. So these are simple TEM images, and initially particles what we synthesize in the hot plate dried at 100 degrees Celsius. These are the raw particles, and these are about 10 nanometer in size. When we heat these particles at 300, 500, 700, and 900, what happens that the surface of these particles get melted. 2 or more particles. If we initially what happens when we heat the particle, surface gets melted, or will be solid, but the surface get little bit melted. And what happens that they 2 or more particles fuse with each other, and the particle size grows. Further heating, if we increase the further heating temperature, it gets further more particles get joined and make a bigger size particles. So we have studied these up to 900 degrees Celsius, and finally got that at 900 degrees Celsius, we get about 100 nanometer size particles. Then we study these properties of these particles. There is one interesting thing that these oxide particles like iron oxide, cobalt ferrite, CuFe2O4, these are already oxide. They are very stable with the temperature. Like iron is not stable. If we heat the iron, it will convert into the iron oxide. If you heat the silver, it will get convert into silver oxide. Okay. So, but these particles are very stable up to 900 degrees Celsius, or even some particles are stable up to 1100, 1200 degrees Celsius. Stability means they are still, their crystalline phase is crystalline arrangement is same. It is not get disturbed. Particle size is growing, but with the particle size, the actual the base of the unit cell is remains same. It is not get oxidized further. Like iron. If you heat iron, it gets iron oxide, Fe2O3, or some other phases also. But from the crystalline, we check their crystalline properties, structural properties, XRD data. And from the XRD data, we can see from the peak position that peaks are not getting shifting towards the left, or peaks are not getting disturbed. But what happens? Peaks are going on sharpening and sharpening as we increase the annealing temperatures. means the crystalline phase remains the same. It indicates the stability of these ferrite materials, magnetic materials at higher temperatures also. You can, these materials at higher temperature, like if you are, there are some materials which cannot be used at higher temperatures, but if you are using these materials, they are very stable up to 900,000 or 1100 degrees Celsius. So, but what happens here, what we can conclude from the graph, that if when we increase the annealing temperatures, then we are seeing there is an increase in the sharpening of these and peaks, and using the simple formula of crystallite size calculation, we have calculated that the crystallite size of the particles heated at 100 degrees Celsius is 6.2 nanometer. As we further increase the annealing temperature, as we have already seen from the TEM pictures, that the particle size grows on, and also the crystallinity now at 300 degrees Celsius, the crystallite size comes out to be 8.5 nanometer. At 500 degrees Celsius, the crystallite size comes out to be 20.9 nanometer. And so on, as we at the 900 degrees Celsius particles annealed at 900 degrees Celsius, the crystallite size comes out to be 24.6 nanometer. These are the basically, the XRD basically calculates the average order of crystallinity within a particle. It is always less than or equal to the particle size, because the whole particle may not be completely a single crystal. There's some cracks within the crystal, which you can improve the crystallinity of these materials by further annealing, or by increasing the annealing time. Like we have annealed for 2 hours. If you anneal these particles for 4 hours, they may get more order of crystallinity. So further, the same cobalt ferrite material, you have these are different size. The particles is same, basic crystal structure is same. It is cobalt ferrite CoFe2O4. There is no change in the phase, but these are the magnetic measurements of the BH curves of the cobalt ferrite particles of different size. Initially, the first curve, the A mark A, first curve on the left corner, it is the corresponds to the particles of 10 nanometer size. The crystal structure is still cobalt ferrite. In higher size also, it is still cobalt ferrite. But the particles of 10 nanometer, you can see that there is no corrosivity or retentivity. Also, the saturation magnetization, the y-axis, it is the saturation magnetization about 18 to 20 EMU per gram. The measurement, the units we have taken is EMU per gram. So as we increase the annealing temperature at 300 degrees Celsius, we have seen the particle size grows and also crystallinity grows. What happens to the magnetic property? What effect? We have seen that there is some porosity or retentivity starts developing in the materials, and also the magnetization, the saturation magnetization has now come out about 30 EMU per gram. So with the further increase in the particle size, further increase in the annealing temperature at 500 degrees Celsius in the curve C, we can see that there is a very large increase in the corrosivity and retentivity. There's you can shape of the curve is very much changed as compared to the particles of 10 nanometer size particle, initially raw particles. So also the magnetization has now become grows the 60 EMU per gram, and the corrosivity comes out to be about say 800 to 1000 Oersted on the x-axis corrosivity measure. And as we increase the further to the 700 degrees Celsius, they are single domain particles about 40 nanometer size, and they have the maximum corrosivity seems to be around 1200 Oersted, and the magnetization is also further increased to about 65 to 70 EMU per gram. As we further increase from 700 degrees Celsius to 900 degrees Celsius, the last the curve E of the BH curve marked E shows that there is some decrease in the corrosivity. However, there is an increase in saturation magnetization. Saturation magnetization have increased from 65 to about 70 EMU per gram. But the corrosivity you can see on the x-axis that there is some decrease in the width of this curve, and that it indicates that there is a decrease in corrosivity. This is because the particles now is converted into multi-domain. Now, how we can say that the superpyramidal particles have zero corrosivity, single domain particles have maximum corrosivity, and multi-domain particles have decreased corrosivity as compared to single domain particles. We will seek their behavior of these particles in different size particles in the magnetic field, how they react with the magnetic field. Initially, the small particles of size about 10 nanometer. This is the behavior of superparametric particles, size range about 10 nanometer in the magnetic field. When we apply, these are the individual particles as an individual magnet of 10 nanometer size, but they are small in size. As we apply the magnetic field, all the magnetic domains get aligned in the direction of field, like every magnetic material does this behavior. But as we remove the magnetic field, what happens that these particles get again randomly oriented, and overall the net contribution, net magnetization of the material becomes zero. So because one particle, there are many particles, and these particles cancel out their net magnetic field with each other. And because the particle size is very small, they 10 nanometer size particle, they can easily get rotated back. As we increase the particle size about 40 nanometer, also shape gets also get little bit disturbed. As we increase the particle size to about, we say that single domain size particles about 40 nanometer, what happens in the initial stage when B is 0, all the particles are randomly oriented. Magnetic moments are of all the particles. Within a single particle, they are oriented in one direction because of their ferrimagnetic nature or ferromagnetic nature. But as we apply the high magnetic field, all the magnetic particle, domains, all the domains, these single domain particles get oriented towards the applied magnetic field. As we reduce the magnetic field to 0, if we initially it is 0, then we increase the magnetic field, then we further reduce. We come back to the 0 magnetic field in the reverse direction. When applied to the, when we remove the magnetic field, means applied magnetic field is 0, then these particles some of these particles try to get to its initial position, but because of their larger size and some little bit random shape, they get stuck somewhere within the in between some other particles. So they don't get back to the initial position, means their net magnetization is not 0, but there's some still in the direction of earlier applied field. There's some magnetization is retained, that we call this retentivity. And we have to apply some reverse magnetic field and high reverse magnetic field to get to the initial position, means to get the magnetization within the materials to 0. So these particles get, some porosity has been developed. And if we compare the porosity of these particles with the multi-domain particles, in multi-domain also this phenomena occurs when in the 0 magnetic field randomly oriented. When we increase the applied magnetic field, the particles get aligned in a particular direction. When we further remove the magnetic field, again, there is the particle rotation is not easy because the particle size is higher. But there is an additional process by which the demagnetization can occur. What is this process? Is that the motion of the domain wall. Domain wall is not a fixed wall. It is flexible, and it can get rotate it can move. Just like you see in when we apply the high magnetic field, the domains in the direction of magnetic field get larger in size. The domains aligned opposite to the field are very small in size. Magnetization or demagnetization can occur by two methods. One, by the particle rotation, if the particle as a whole may get rotated, or second, another process is the domain wall may also move. So they are, even if there is magnetization or even if there is demagnetization, in spite of in single domain only, there is one option that only particle has to rotate back, because within the particle all the domains are aligned in the single directions. All the magnetic moments are aligned in the single direction. But here demagnetization can occur by two processes. One is the particle rotation, which is relatively little bit typical. Means require higher energy. We have to apply higher magnetic field for that. And another is the domain wall motion, which is relatively simpler. So with the application of smaller magnetic field as compared to the single domain particles, the particles get the magnetic moments get randomly oriented, and because of this we get the reduced porosity in the multi-domain particle as compared to single domain particles. Now, what is the reason behind the reduced magnetization? You have seen that larger size 100 nanometer particles of cobalt ferrite have a saturation magnetization of 72 EMU per gram, and the particles of 10 nanometer size have magnetization of 18 EMU per gram. So about 4 times reduced, magnetization is reduced about 4 times. So what is the reason behind it is that in almost all of the magnetic materials, the surface layer acts as a magnetically dead layer. Means even if the particle is magnetic, like iron or inox, Fe3O4 or cobalt ferrite, the particle's inner core is contributing towards all the magnetic moments are aligned in a direction. But the surface layer of about what thickness? About 0.5 nanometer. Surface layer of about 0.5 nanometer have its magnetic moments in the surface layer. The magnetic moments are not aligned in a single direction. Just like in a domain, all the magnetic moments are aligned. But even if in the magnetic materials, in all the magnetic materials, surface layer acts as a non-magnetic. It's the magnetically dead layer. And as we reduce the particle size, more and more contribution we are getting from the surface. Okay. Because if we break a particle, we get within the similar volume, same volume, we got increase the surface area. So when we increase the surface area, surface contribution will increase, and surface layer is magnetically dead. So as we reduce the particle size from 100 nanometer to 10 nanometer, the magnetic saturation magnetization will go on decreasing, as we also observed in our studies of the cobalt ferrite nanomagnetic particles. Now, magnetic fluid we have already defined, and this is the most interesting slide, basically, which can be used for the application point of view of, and I've also used this slide for the design development of many devices. And what it indicates that within a 1 millimeter thickness, because in magnetic fluid, the particles are about 10 nanometer size, surfactant layer is about 2 nanometer size. So within a 1 millimeter, particle size is about 10 nanometer. Within 1 millimeter, there are about 1 lakh layers of nanomagnetic particles. And because of the surfactant property is that the tail of the surfactant repel each other. Okay, one surfactant coated on one particle repels the surfactant coated on the other particle. The tail of these gas repels. So because of this repulsion, we get some frictionless layers. A set of friction layers within a 1 millimeter. There is a set of 1 lakh frictionless layers which slide over each other very easily. And the coefficient of friction we have calculated. The coefficient of friction we have calculated within these layers comes out to be 0.0008 mu s, coefficient of static friction. Means at some angle, if we how we are holding this magnetic fluid, we are taking a permanent magnet. You are seeing something green in color, parrot color, and above black in the lower diagram, you are seeing a black layer above the permanent magnet and below the permanent magnet. So because the magnetic strength is highest in this magnetic fluids automatically get attached to the permanent magnet, and it remains mostly of its the content remains at the poles of in the North Pole and the South Pole. They make bearing like these black bearings. They make these bearings, and when we studied the coefficient of sliding, coefficient of static friction, we put our magnet fluid bearing on a flat surface and start tilting from one side, making measurements with a digital screw gauge. And we have seen that with a tilt angle of 0.04 degrees Celsius, it starts sliding. The friction is as less as than 40 times within the friction between two ice cubes. Ice cubes are very slippery. Two ice cubes are very slippery, and the coefficient of friction is here even less than that friction. So using this property of magnetic fluids, that they get attached with the permanent magnet, and the coefficient of friction they are providing is very small, about we have calculated 0.0008. So with these properties of these magnetic fluid bearings, we have used this property in the design and development of many devices. Initially, we have studied for the design development of in the electric power generation. We have taken alternate magnetic poles, south, north, and put the ferrite fluid bearing on these poles, opposite poles, both the poles. And what happens that this bearing have now made the motion of the permanent magnet very easy. And in upside and downside, we have put the coils, and with a small force, with a very small torque, if we want to rotate these magnets, or we want to shake these So they require very small force because the coefficient of friction is very small. Coefficient of friction is, we can say, negligible. So you can say that they are just like moving in the air, simply air. So the coefficient of friction is very small, and we have taken the alternate combination of these permanent magnets. So as we move, apply a little bit force, the magnets start moving left and right, and as the coils are fixed in the design. So coils are fixed and magnets are moving. So there is a change in the magnetic flux, and with the change in magnetic flux, we are getting the electric output from this design. And this concept we have utilized in the development of these wind turbines, and similarly the alternate fashion, but here we are now rotating these with the help of some shaft attached with the wind blades of the wind turbine. So what happens, how it is different from the conventional wind turbine is that in the conventional wind turbine, shaft has to carry the weight of the heavy magnets. The shaft in the conventional wind turbines, the weight, there are very much heavy magnets are there, and this shaft has to carry the weight of heavy magnets. But here the shaft doesn't need to carry the weight of these permanent magnets. Our magnets are now sliding on the magnetic fluid bearing, and the coefficient of friction is very small. So now the shaft don't have to carry the higher weight of these magnets. The shaft only have to rotate these. So what happens, the input wind power, this is the formula written in blue in color. Wind power is equal to torque into 2 pi into rotation speed. So in spite if the shaft had to carry the weight of permanent magnets like presently in the conventional wind turbines, it requires higher torque. If you have to rotate a higher weight, then you need higher torque to rotate this higher weight. But now the weight has been rest on the magnetic fluid bearings. Only you have to rotate. So just like you have to rotate on the wheels, in spite of carrying your high weight and rotate, take in your hands and rotate it, you require higher torque, need higher torque. And you can reduce torque by if we rotate it on wheels. And the wheels, if the friction of the wheels is very small, then the amount of torque has been reduced. And using the same input wind power, we can increase the second part, rotation speed. Second part of the formula, by reducing the torque and using the same input wind power, you can increase the rotation speed. So what happens that if we increase the rotation speed means you have increased the change in the rate of change of the magnetic flux in the magnets. Because if the magnets are rotating at a higher rate, then it means the d phi by dt is increased. Or if d phi by dt means you are increasing the EMF or output of the generator of the wind turbine. So this is the design we have developed, and we have also patented. Patented means this is the first time in the world, and I think we must strive for its commercialization also. So this is the efficiency we have calculated at different wind speed, available wind speeds, because we have developed, we are studying in our laboratory by using, wind speed we have generated by using a simple fan, and different wind speeds we have taken 1.7 meter per second, 2 meter per second, 3 and up to 4 meter per second we have studied. And the efficiency we can see from the graph that with the wind speed, efficiency goes on increasing. And at 4 meter per second, we are getting efficiency of about 24%. 24% means if the input wind power we have calculated by the formula, above formula in the P is equal to 0.5 rho V cube A. Rho is the density. If we are taking air, then density of the air, it's about 1 and 1.225. And V is the velocity of the wind. A is the area of cross section of the, how much area of cross section we utilize in our design. So input wind power, if we are taking 5 watt at 4 meter per second, we are getting output electrical power. Input wind power is what is? It's wind energy, and output energy is electrical energy. It's 1.2 watt or 1200 milliwatt. So the efficiency is, we have calculated is 24%. Conventional wind turbines have at 4 meter per second, they are even less than, I think, 10% efficient. And the wind turbines have maximum efficiency of about 9 meter per second. But in our laboratory, we cannot develop such a high wind speed, because this high speed, we have to go to some hilly top and In laboratory, we have studied this up to 4 meters per second. It's 24%. Expected that this curve will go up to at least 40-45% at 9 meters per second. So conventional wind turbines have about maximum of 20% at 9 meters per second wind speed. So this is expected to be have higher efficiency, quite higher efficiency as compared to existing wind turbines. So it may got application in the future development wind turbines also. So another device we have, this is the patent of this, and the device we have developed is these are very simple devices, not very much typical. Just you have to think some design which is can get some applications. This is a simple glass design, simple glass bulb of about 115 milliliter. Randomly we have taken some about 115 milliliter, and we have taken firefoot bearings. You can see that inside above tube, you can see some black and some magnetic fluid bearings, black firefoot bearings. And these, what happened, because these are frictionless. There is no other piston which can be used for here, because a rubber piston or something, these piston corks, these are not frictionless. They get stuck within some area. And if you use, and also there is leak proof, because the magnetic fluid bearing is providing two main components here. One is frictionless, one is leak proof. It doesn't allow the air inside this bulb, below bulb, 115 milliliter, to it doesn't allow the air inside this bulb to escape from this bulb area. So what happened, as we increase, as the temperature of this lower bulb is increased, air by naturally it gets expanded by PV is equal to nRT. If we increase the temperature, then volume will also increase. And also because this firefoot bearing doesn't resist towards this, because there is no friction, and this also leak proof. So what it responds even to a very small change in volume, very small change in pressure. So if due to increase in temperature, pressure inside the bulb increases, it moves this extra pressure moves this firefoot bearing wall. And what happens when iron rod is attached with this permanent magnet with firefoot bearing, and when iron rods comes in between there are two coils also, primary coil, one is the secondary coil. In primary coil, we have put the input 5-volt AC, fixed input we are using a small transformer, and output we are taking into the multimeter. As the input is fixed, initially what is there is an air core. There is no iron core, the location of iron core is downward. As the temperature is increased, the iron core, more and more portion of the iron cores get inserted between the primary and secondary. And as the iron core is inserted between the primary and secondary, mutual induction will increase. And because the input, primary coil input is fixed, but due to increase in mutual induction, the output at the secondary coil will go on increasing continuously. As the temperature rises, the firefoot bearing goes up, and with the firefoot bearing permanent attached with the permanent magnet and some iron core attached with also iron core get more and more inserted between the primary and secondary, which increase the mutual induction and overall increasing the output of the device. And the efficiency of the accuracy of this device is very high. With the response of this device is very good. With we have taken temperature of 30.2 degrees Celsius to 30.5 degrees Celsius. Initially, what we have taken a capillary here, physical measurement. Then we have done its electrical measurement in this below design. In the above design, we have taken physical measurement. We have taken 1 meter and 0.5 millimeter capillary, in which we have taken some liquid column, because liquid can stay inside the capillary. And with the increasing pressure, this firefoot bearing moves upward. And when it moves upward, this liquid column responds to this increase in pressure, and it also moves upward. And with the change of less than 0.5 degree, the change in the scale of the capillary scale, the liquid column, it's about more than 70 centimeter. So the sensitivity of this device is very high. You can guess that half degree mercury thermometer with an increase in 1 to 1 degree Celsius, there is very little change in the mercury position. But here, with the change of 0.3 degrees Celsius temperature, there is a change of about 70 centimeter. So you can guess because what is the reason? Because it is using the air expansion. Mercury thermometer is using the using the expansion of the mercury. And in air, the expansion is about 20 times higher compared to the expansion in the mercury. So the sensitivity of this thermometer is very high. Then we had done the electrification of this device using the same concept I had discussed in the earlier slide, that we have put primary coil and secondary coil. And with the increase in mutual induction in between the primary and secondary coil, we are getting the higher output. And here we have taken the change of 1 degree Celsius from 26 degrees Celsius to 27 degrees Celsius. This output reading is in millivolt. Millivolt can be measured very easily using a simple multimeter of 200, 500 rupees. So from the change in 1 degree Celsius in temperature, we have seen that there is a change in output of from 200 millivolt to about 600 millivolt, 400 millivolt. There is a change of about 400 millivolt. So we can say that the sensitivity of this device is 2.5 millikelvin per millivolt. 1 millivolt can be measured easily. So if 1 millivolt change can be measured, then you can measure a temperature of change in temperature of 2.5 millikelvin using this very simple device, okay, with very high accuracy. Now, here we have made also using the same nanofarad bearings. We have anti-vibration table we have developed and also patented. And what we have taken here, the permanent magnet, same the permanent magnet farad bearing, and we have choose this alignment in the repelling position. The lower magnets attached with the base are aligned in repelling position with the middle magnet at the middle, and also magnet in the middle has been used with the farad bearing. So what is the role? It's leviated. It's the upper layer is leviated in air, and the farad bearing attached also reduces the vibration component of the created in the base to reach at the about top of the device. So it's also patented recently and using the same low friction magnetic bearings. We also patent some this device also vibration sensor. That is a vibration isolation. It is a vibration sensor device. So this is also very sensitive device because you can see the same repelling magnet concept you had taken. Base magnet has been fixed, and the magnet at the middle you can see in between the coils with farad bearing. This is air leviated and with a very small vibration, because it is air leviation is in air leviated with a very small vibration, because it is free in air and also there is no friction problem. So it is free. No, there is no friction has been. So it responds to very small vibration, and means how it responds. Magnet also start moving with respect to the coil, and with a very small motion of the magnet related to the coil, some electricity will be generated in millivolt signals will be generated. And if the amplitude of vibration is higher, you get a higher millivolt signal. If the amplitude of vibration is smaller, you get the smaller millivolt signal. If the frequency is higher, you get output in higher frequency. If the frequency of the vibration is lower, so you get a relative measurement with the at the output of the device with respect to the vibration. You can measure the very small vibration. Even it is put on the table, you can tap of your finger, you can sense if the background noise is suppressed. So the sensitivity of the device, these devices are very much sensitive to than the existing, but they are still not at the stage of commercialization, because some industry has to take on forward step for this to commercialize these devices. So, but the sensitivity of these devices is very much high. Even this sensor, vibration sensor, is very much high sensitive compared to the standard sensor used for the calibration of the vibration sensing purposes. So piezoelectric based sensor, there are some piezoelectric based sensor, but this sensor have very much high sensitivity as compared to standards which are in market. So we are hopefully we will also get the future product in the market. This is all the same concept using the low friction magnetic fluid bearing and iron rods we have attached in the both side, and we have designed an acceleration sensor using the primary and secondary coils. So similar, if accelerate or deaccelerate is it's now horizontal position, the device is put at the horizontal position. If there is some acceleration or some deacceleration, the magnet will move, magnet attached with the felt bearing will move very easily, respond to the acceleration or de-acceleration. If there is an acceleration, magnet will move backward. If there is de-acceleration, magnet will move forward. And with the backward or forward motion of the magnet, there is a change in the flux between the primary and secondary coils shown above and below the tube. So when there is a change in flux, there is some change in relative voltage in between the left side coil and right side coil. So we'll get an output even with a very small acceleration or de-acceleration. So this device can also be used for the commercial application. This is the output of this device with respect to acceleration. We have calculated in terms of G, we have defined the acceleration 1G, 2G, 3G, up to 4G. We have defined up to 5G. G means acceleration due to gravity. G value, that is the G. So with 1G, 2G, 4G, and 5G, we have calculated and find that the change in position of this permanent magnet. The first column shows the change in position of this permanent magnet in centimeter or millimeter in centimeter, and the second column shows the output generated in terms in millivolt signal at the secondary coil. So you can see that this output is in the range of 212 millivolt, 400 millivolt range. So this range can be measured with the help of a simple multimeter. So this is also designed. This is also further we want to increase the efficiency of this acceleration sensor device using the magnetoresistance property. Also, we want to reduce the size of this device. So in spite of air compression or expansion, now we have reduced the size of this and put two, in spite of taking the primary and secondary coils, we have put two silicon N-type or silicon or germanium wafers, and using the concept of magnetoresistance, because when there is some acceleration or de-acceleration, the magnet will come towards one of these two silicon chips and go away from one of these two silicon chips. So if we accelerate, it come closer to the backward silicon chip as compared to the forward silicon chip, and if there's de-acceleration, the magnet will come towards the right hand side of this chip and go away from the left hand side of this silicon wafer. So as the magnet moves, and due to the property of magnetoresistance of the silicon or doped semiconductor metals, so there is a change in the electrical output. The resistance of this will change. This chip will change. One of the resistance of one of the silicon chip will increase, and one of the other silicon chip resistance will decrease. So there is a change in resistance, and change in resistance means you can measure using this change in resistance with the help of multimeter, and you can sense the amount of acceleration relatively terms. You can sense the amount of acceleration or de-acceleration. You get the output in terms of electric. This is the self-cooling device. Professor Sane also discussed about this in the morning lecture. And this we can, without the use of external energy, what happens that we have to, for the cooling purpose, we have to flow some fluid. Fluid may be air or it may be some liquid. But the pump, we have to apply some energy to the pump so that to flow that. But here, with the help of magnetization or demagnetization, magnetic response with temperature of magnetic fluids, so this fluid will automatically flow. What input we are taking, there's some temperature gradient because of some heating device. Temperature gradient will already be there naturally, and using a permanent magnet, because the magnetic fluid we have filled in this tube, and as when magnetic fluid come in contact with the heat load, for example, your car engine or some heat load, anything. So when the fluid come in contact with the fluid which is in contact with the heat load loses its magnetization, because at higher temperature, as the temperature increases, magnetization decreases, and at certain temperature it becomes non-magnetic, also pure temperature, you could say that. So with the increasing temperature, its magnetization decreases, and there is some fluid also there in the tube which is at lower temperature as compared to the fluid in contact with the heat temperature. That fluid will come in near with the magnet, because that have the higher magnetization, and the fluid in contact with the heat load will have the lower magnetization. So there is some circulation of the fluid automatically, just with the because of their magnetic nature, decrease or increase in magnetic nature. And when during circulation, when we the fluid come in contact with the heat sink, it liberates heat and become cool. And again, when it become cool, it will want to come near to the magnet. And when it come near to the magnet, it will come in contact with the heat load, and for the heat, the fluid reduces. The magnetization of the fluid reduces, and it will move upward, and cold fluid will move automatically towards the magnet, and so on. The cycle goes on changing. And this is the device which one of our students have studied this application. And this is the basic phenomena, that the concept that is used in the design is that this empty curve, we have to take measurement of this empty curve, and we need a higher slope. We can develop better self-cooling device if we get some material for the magnetic fluids. We want to increase this delta M by delta T slope. If the slope will increase, our efficiency of the device will increase. So presently we have studied with using the magnesium ferrite fluid Mn 0.5 Zm 0.5 fluid based upon this material. And because magnesium have response of this material is seems to be higher with temperature. Temperature response is higher, means there is larger change in magnetization with temperature. There may be some other materials also which may respond more better. So that's a part of research, and everyone can proceed in this direction. This is also a concept, but this concept we are planning to utilize. Not up to now, we have not utilized, but self-refrigeration. Some of the in the worldwide, some companies are there which are working on this designing of the self-refrigeration with the help of magnetic field, in spite of using the compressor expansion, because some chlorofluorocarbon hazardous gases are used in the compressor of the fridges. So this can be used, the cooling can be achieved also with the help of magnetization or demagnetization, and some of the companies are doing work, and some lab models have also been developed. The concept is behind this device is that when there is we are using only magnetic materials and magnetic field for cooling, and for cooling we are using only two things. One is the magnetic material and one is the magnetic field. When, for example, this block is the magnetic block, and when there is some B is 0, then magnetic moments are aligned randomly. When we increase the temperature, when we apply the magnetic field, when you apply the magnetic field to this magnetic block, all the magnetic moments will get aligned in one direction. But what happens when the magnetic moments get aligned in one direction? This is somewhat a typical condition for the magnetic material, and it will increase the temperature of this magnetic material because some energy has been applied to the material. And to keep these domains in one direction, some force is continuously running, and the temperature of this magnetic material will increase. Now, as this magnetic material is in contact with the surrounding, in contact with the atmosphere, so in a little time it will the contact or the temperature of this magnetic block will come out to be equal to the atmospheric temperature. But when we remove this magnetic field, what happens? That magnetic moments get randomized, and when these magnetic moments get randomized, the temperature of this block will decrease below that atmospheric temperature. So with the application of magnetic field and with a small weight, so that the magnetic block temperature will come out to be atmospheric, near to atmospheric temperature, and further removing the magnetic field, we can cool some these magnetic materials. But metal to metal, there may be different efficiencies of the device may work on the may depend upon the type of these materials and properties of these magnetic materials, and also on the amount of magnetic field we are applying. This is the micro valve and micro pump. We have also developed the micro valve and micro pump using the magnetic fluids with magnetic fluid, but we have taken it's a little bit when there is some micro in MEMS devices or in NAMS devices, the size of the device is very small. So, for example, in our injection, it's about millimeter size. So we use a piston, rubber core for the injection, for the movement of the liquid in the injection. Or if there is further small capillary, so the piston, use of the rubber piston is not advisable, because rubber piston, if the length of the capillary is very large, then rubber piston you have to attach some mechanical part, and the motion is not so free. You have to apply some force also, if it get attached with some moving component. So using a magnetic fluid, this design, we can allow or block this fine capillary any gas or any liquid flow. We can block the flow of any gas, or we can allow the flow of any gas with the help of external magnet. Because we can, using the magnet position, you can move the liquid magnetic fluid inside the capillary. And if you see the first and second diagram, in the first diagram, air can flow from left to right. But in the second diagram, using the external magnetic field, we can block the flow of air, especially for the micro level devices, because where we cannot use the rubber core or any other pistons. So the burst pressure we also calculated, it's come out to be about 95 millibar. How much pressure that can hold, because it is liquid, it is not now solid. So it is a limitation that it can hold a maximum pressure. If the pressure is very high, the liquid bearing may get spread out. So burst pressure we have calculated about 95 millibar for this device. Micro pump, for micro actuation, if we have to put some micro level drugs from one position to other position, then this device we have developed the micro pumping with the actuation of left motion of the permanent magnet green in color, and with the felt fluid bearing with the motion with the left and right, we can actuate some liquid and deliver at the output. In about, we had done this per actuation, we had done delivery of the liquid. For example, some drugs we have to deliver in very small quantity. So about in 10 microliter per actuation, but some electrification we have to do. So this device, using this design, we can achieve this micro actuation also. So these are all the devices are very low cost device, and I think can just you have to design in your mind some device and continuously seeing the working of the devices. And one of the material have been used for the humidity sensing purpose, our GD doped cobalt ferrite we have taken. It's a solid metal pellet we have taken, and these materials, ferrite materials, are porous in nature because they are nanoparticles, and there's some pores when we make pellet of the materials. There are very large number of pores are there, and these pores bond with the environment humidity, and with the increasing humidity level of within the material, their resistance will change. And on the base of the electrical conductivity, or on the base on the change in resistance, we can measure the environmental humidity. So we can take the sample which is the more sensitive towards the humidity. So one of the samples we have studied GD doped cobalt ferrite, and it's very show good efficiency with because its conductivity, it's a relative measurement. Conductivity changes with the environmental humidity, and we can measure the environmental humidity with this material. So one of these ferrite materials has been used for the sensing of the alcohol, ethanol, methanol. We have taken in our measurement, we have taken 3% methanol. With humidity, the resistance will also change. Like you can see from the curve that with the resistance versus response time curve, you can see that with humidity also they change, decreasing resistance. But in spite of water vapors respond very slowly. You need more time. In about 1,000 seconds, the resistance decreases. But if in case of methanol or ethanol, water plus 3% means there is 100 ml water and 3 ml methanol. So at room temperature, if this solution come in so the solution, if the put our sample just above this solution, there is a very large dramatic change in the resistance from 76 kilo ohm to about less than 20 kilo ohm. So within a fraction, about 3-second response time we have taken. So within 3 seconds, there is very much large change in the resistance. And based upon this change in resistance, we can use these materials for the alcohol sensing devices. So these are the some of the applications we have studied. And very thanks for all of you for hearing patiently. Now, any questions you may ask?
Thank you, Vinod. Any question from the audience? Any query? Anybody want to ask anything related to what Dr. Vinod has said? Vinod, it was a wonderful lecture. By using only two property, one is a flow or fluid, and the second is magnetic. You have shown us a number of applications. Wonderful. It was really wonderful.
You can contact further if you seem interesting, and any audience can contact anytime.
Yes, sir. I will share your email ID and number in the chat box. So, sir, the audience is asking, can you share your presentation? Okay, we will share it. And one thing, this lecture is also available on YouTube. I will share the YouTube link in the group. So later on, you can see all the slides from that YouTube link.
The work is simple. Also, I want to communicate to audience that the work is very, if you think that research is something, some of the in colleges or somewhere the facilities are not much, but they can do research there also if they are interested. The only thing need is the interest of the candidate, everyone. So can do any research work with the help of mine. So very thank you to all of you.
Okay, thank you very much. Thank you, Vinod. Okay, Ashok, now you can take over.
Thank you. Thank you, Dr. Vinod.
Thank you, sir. Thank you very much, sir. Now,
well done, very good.
Stop. Yes, sir. Thank you, sir.
हाँ, अशोक कोई अनाउंसमेंट है क्या?
हाँ जी,
अशोक
सा था अभी था ही.
अच्छा, is there any announcement this we should quit or not?
एक मिनट सर. अशोक का
चलो वो व्हाट्सएप पे कर देगा.
अशोक का लिंक तो टूट गया सर. अशोक था अभी.
हाँ, कोई नहीं, उसने कुछ कर दिया.
उसको कोई होगी अनाउंसमेंट तो कह देगा, तो कल हम फिर मिलते हैं.
हाँ, वो व्हाट्सएप पे ग्रुप पे कर देंगे. ठीक है.
तो ये ठीक है, फिक्स ही है मतलब टाइमिंग. तो
ठीक है. ओके.
ओके, थैंक यू ऑल.
ओके. मीटिंग एंड कौन करेगा? विनोद भाई. विनोद,
मीटिंग का कैसे करें? लीव करेंगे तो शायद हम जाएंगे.
नहीं, डॉक्टर अशोक प्रेजेंट है.
अच्छा, अशोक सर कर देंगे.
डॉक्टर अशोक प्रेजेंट है, तो वही.
ठीक है. विनोद भाई, बड़ा अच्छा था एप्लीकेशन पार्ट. इसका न्यूक्लियर में कोई एप्लीकेशन है क्या इसकी?
और न्यूक्लियर में तो नहीं
भाई. रिएक्टर वगैरह में तो कोई काम आ सकता है कि अच्छा है फेरोफ्लूइड
वो, लेकिन वो न्यूक्लियर की एप्लीकेशन साइलेंटली करनी पड़ेगी, वो पता नहीं है.
अच्छा.
सेंसर में तो है डॉक्टर विनोद.
हाँ जी.
सेंसर में तो है, ह्यूमिडिटी सेंसर है, गैस सेंसर है.
हाँ, सेंसर
बिल्कुल है. सेंसर में
बेसिकली हम लेक जो करते हैं ना, डिवाइस मतलब कंसेप्ट देके आगे चुप बैठ जाते हैं. चक्कर वो है, आगे कोशिश नहीं करते. डिवाइस वो थोड़ा सा भागदौड़ी करनी चाहिए.
डिवाइस बन जाए तो बन जाए.
कंपनी के साथ वो कंपनी के ही पास पॉसिबिलिटी होती है, उनके पास औजार होते हैं रिलेटेडली. तो कंपनी थोड़ा सा मोटिव,
कोई इंडस्ट्री के साथ होना कोलैबोरेशन, कोई इंडस्ट्री में पीपल होना, कोई ठीक
तो प्रभावित करना पड़ेगा. एक के साथ तो कर पाती थी, लेकिन
ये है तो पेटेंट है.
बात हुई थी इंडस्ट्री के साथ वाइब्रेशन सेंसर.
हाँ जी सर, मेरा डिस्कनेक्ट हो गया था सर बीच में.
हाँ, इसको हो गया, कंप्लीट हो गया आई थिंक.
हाँ ना.
बहुत बढ़िया लेक्चर दिया विनोद ने.
थैंक यू विनोद सर, एंड
थैंक यू जी.
थैंक यू रजनी मैम फॉर चेयरिंग दिस सेशन.
वेलकम, मोस्ट वेलकम.
Thank you, ma'am, and thank you very much to all the participants for attending all the sessions with full patience. And I think you have learned a lot about kinetic nanoparticles and about the nuclear techniques used for the elemental analysis during these two sessions. During these afternoon sessions. So thank you very much for being with us. Again in the morning, the session will start at 10 a.m.
Hello.
Problem है ना sir?
आवाज क्लियर नहीं है सर
Yeah, Professor Vinod, I would like to ask you a question.
Yes, sir. Yeah, sure,
Is
sir.
it okay?
Yeah, sure, sure.
Yeah.
Yes, sir.
See, my name is Sridhar Babu. I am working with BML Munjal University.
Sure.
Okay. Yeah, this ferrofluids really it's very interesting. So can you please share the minimum minimum experimental facilities required to start a research in this area?
Yeah, sure, sir. It's the starting is not much costly, sir. I think about developing nanoparticles, maximum cost you have to initial cost you have to 25,000. You can develop nanomagnetic particles and magnetic fluids. You can start on this. Further, with your experience, you can develop fluid. Making fluid is somewhat tricky, sir. It needs some trick little bit. But making nanoparticles, you can within some chemicals, 5 to 10,000 cost about chemicals, and hot plate you require little bit some, and within less than 20,000 you can develop nanofarad particles, sir, of different size. Okay. Then you can add some furnace also, furnace 30-40,000 you can get furnace, and further if you can start, it is very not so much costly, and little bit small components you may add. They are you can arrange easily, sir. At your university you can arrange easily. So not much cost is not much involved. Just only interest is there, and fluids you can magnets are also available in the market, and fluids you can make in your lab also. Otherwise, also available in the market also, but not India. In India, not it's some US is making good magnetic fluids. So Indian made fluids are so much if you are using some for commercial application. So the cost is not a factor, sir. Yes, so you can contact in future also.
That's great, sir. That's great.
Yes, yes, sir.
Yeah, your talk was really excellent, and then the kind of applications you presented really very interesting. Even I think most of the participants are also inspired by your work. So
very
if
thanks,
possible,
sir.
I may be in touch with you, and I will
sure, sir, sure.
see you also. You're in Delhi,
sure.
I am in Gurgaon only.
Yeah, yes, sir. Yes, sir. I would like to just shift after. Presently, I'm here, sir, but I may shift in the coming days, sir. Yeah. Thank you, sir. Thank you.
Okay. Thank you very much. Thank you very much.
Dr. Surinder. फिनिश करें सर आज का. पार्टिसिपेंट्स अगर आपका कोई क्वेश्चन है, क्वेरी है तो आप पूछ लीजिए प्लीज.
नहीं सर, अभी कोई क्वेश्चन नहीं है सर.
संदीप ने वाइंड अप कर दिया.
मैं पार्टिसिपेंट, कोई क्वेश्चन नहीं है सर अभी मेरे पास.
एक क्वेश्चन पूछने चाहिए, थोड़ा एक्टिविटी लगती है वैसे.
नहीं, अच्छा था ये एप्लीकेशन पार्ट आता है मैडम, तो उसमें साथ में क्वेश्चन साथ हो जाते हैं एड्रेस. अब मान लो कोई ऐसा कोई फार्मूले थ्योरेटिकल ऐसा ग्राफ दिखाए ना, वहाँ तो कंफ्यूजन सा रहता है, पता नहीं क्या बताया.
इसमें ऐसा होता है इन जनरल जो हमें आता होता है हम बता ही चुके हैं, मतलब देखा जाए तो.
नहीं
तो आगे तो फिर वो वर्किंग एंड आ जाता, फिर तो वो आ जाता है कि तार लगाने हैं, फिर वो करना है.
सब टाइम ना सर कंसेप्चुअल बातें रह जाती हैं, लेकिन वो बातें फिर यहाँ भी नहीं सकती. चलो एक दो हो सकती हैं, कंसेप्चुअल बातें तो पढ़ने से आएंगी, बाकी इसमें तो ये आइडिया देते हैं.
मतलब
ये है सर का मेल और नंबर मैं शेयर कर दूंगा ताकि किसी को कोई डाउट हो इन फ्यूचर.
यस.
एक और चीज कहना अशोक सबको कि अपना माइक ऑफ रखें, बीच में माइक ऑन होता है तो वो
बस इसका आज मैम मैंने ना कुलदीप को बोला था,
बुरा लगता है
वो म्यूट करने. आज मैं उसको दोबारा बोलता हूँ क्योंकि ये हैंडल सिर्फ कंट्रोल हमारे पास इसका आ जाए ताकि कोई अपने आप इसको अनम्यूट ना कर सके. तो आज इसका सोल्यूशन करवाता हूँ मैं।
हाँ, और हैंड रेज करें उनको, उसके बाद आप लोग उसको
हाँ,
कर
उसके
सकें
बाद
बताइए,
अपना किसी को भी। हाँ
वो
जी,
भी
मैं
जो
वही-
क्वेश्चन सेशन में ऐसे
कुलदीप
नहीं।
है शायद लिंक में, कुलदीप।
अब नहीं है डॉक्टर साहब।
हाँ अब नहीं है। चलो ठीक है जी, सभी का धन्यवाद।
हाँ, ये अशोक सर, ये माई गजल कह रही है कि सारा मुझे आता, मैं कर दूंगी, ये मतलब अब
कर
ये
देंगे।
एक्सपर्ट हो गए, बच्चे एक्सपर्ट हो गए, ये 2 साल से ये लगा रहे हैं जो उम्र को गर्मी।
हाँ, कल वो रविंदर सर का बेटा भी यही बता रहा था कि यहाँ से को होस्ट बनेगा, यहाँ से।
हाँ, मैं कह रहा हूँ ये हमारे से ज्यादा एक्सपर्ट हो गए, मेरा नाम जो किसी ने किया है फिर ऐसे बदला जाएगा ये, पहले मैं कर ले।
चलो
नेक्स्ट
इसको
टाइम ऑर्गेनाइजेशन में उनको ही डाल देंगे
टेक्निकल जो है ना, वो वही देखेंगे।
अशोक सर और वो मिलके ने टीम में वो होंगे इनके साथ।
चलो ठीक है सर, थैंक यू वेरी मच, थैंक यू
जी
विनोद
सर,
सर,
जी
एंड थैंक यू
नमस्कार
ऑल।
साहब,
ओके सर, गुड इवनिंग।
गुड इवनिंग साहब।
Good evening.